Okay, so I suppose I'll get started. I welcome you to this problem solving and live interaction session for the course Experimental Stress Analysis offered by Professor K. Ramesh. My name is Ganesh Ramaswamy. I'm a PhD scholar in the Department of Applied Mechanics, working with Professor K. Ramesh, and my co-guide is Professor U. Saravanan. So we'll get started. If there are any questions from what we have discussed so far, you can ask. Otherwise, I'll proceed with solving today's question. Understandably, we have a quiz tomorrow, so I suppose many have not many are busy preparing for that, so that's fine. But anyway, I'm uploading these video sessions to YouTube also, and the links are available in the SWAYAM portal on the left side bottom, in case people want to refer back to it. Okay, so I'll get started with the first question. Basically, today's session is more to do with optics and crystal optics and birefringence, some fundamental principles that are observed and which are exploited in the development of photoelasticity. So the first question says Maxwell's electromagnetic theory predicts the presence of two vector fields in light waves, namely the electric field E and the magnetic field H. Identify the correct statements in this regard. So the electric field and magnetic field have a phase difference of pi and are mutually perpendicular. The electric field and the magnetic field have a phase difference of pi by 2 and are mutually perpendicular. Both these fields are in phase and are parallel to each other. Both these fields are in phase and mutually perpendicular. So it's fairly straightforward. We have been seeing this since high school. So the idea is that if this happens to be one of the fields represented by one of the fields, the other field is perpendicular to it. Perhaps I should have drawn it in a different color, but it's okay. I suppose that is understandable. So these are in a different plane. If the electric vector is in the horizontal plane, then the magnetic vector is in the vertical plane. Both are mutually perpendicular and they are in phase, which is what causes it to propagate. So clearly the answer to this is D. Okay, so let us look at this one. The given figure represents the output light intensity of a light wave after passing through a polarizer and analyzer combination. Now, polarizer and analyzer are basically one in the same. The thing is, it is a special kind of material or a sheet made of a special kind of optical response, which allows only one direction. For example, if this is an analyzer or if this is a polarizer, and if it has a direction like that, it implies that only direction light vectors that are parallel to this direction will be transmitted through that. Light vectors in any other direction will be cut out. And naturally, the light vectors that are in this direction, they do not go totally unaltered. So they get absorbed also. So that is why polarizers, if you see the specifications, it will come with some tolerance of transmission. So naturally, whatever light is incident on the polarizer and what is seen on the other side, it will be a bit dim because some of the light even in that direction gets absorbed. But the speciality is that whatever is passing is only parallel to this axis. This is the polarizing axis. So generally, when we buy these sheets, they will have it marked. In general, if we buy the sheet, it will be parallel to one of the sides. But even otherwise, we can simply figure out if we have a polarizing light source, we can rotate it and easily figure out what is the direction of that polarizer. So there's something I just wanted to clarify before moving forward. So polarizer and analyzer Analyzer, because in essentially in photoelasticity we are using light as the sensor. Light is what we are measuring. Generally, in other methods, we will be measuring stress based, we will be calculating stress based on measurement of strain or displacement. In photoelasticity, we essentially, in transmission photoelasticity at least, we measure the light intensity and directly calibrate it to the stress patterns instead of going through that the other route. So essentially, light becomes our sensor. So we should know how to be able to control it in order to clearly demarcate what is the difference in the light that has been brought about by the model behavior, which is under study. Okay, so with this background, let us read the question. Initially, the polarizer and analyzer were kept parallel to each other, and then the analyzer was slowly rotated by 90 degrees, keeping the polarizer stationary. Arrange the following figures according to the increase in the angle between analyzer and polarizer. Enter the alphabets without separating by commas. Of course, this is pretty straightforward. What is to be, how it is to be reported, that you can just follow. Just what this question is trying to ask is if we have a light source. And then let us say that is the light path we are considering. And we have a polarizer. That is essentially this sheet is placed over there. And we have an analyzer also, which is another polarizer, but we will name it as A. This is our reference axis. Now initially they are kept parallel. So we know that here in this zone, let me call this zone number. In this zone, we will have unpolarized light because the light source as such, it is not mentioned what it is. So we can take it that it is unpolarized, which is why we are trying to control it by polarizing it. Then in this region, we will have linearly polarized light, which is parallel to the polarizing axis. And what we see out of this end is what is given in the question. So initially when it is parallel, naturally whatever light that is impinging on the polarizing sheet, only the vertical passes through that. And since the analyzer is kept parallel to that, it will directly pass and we'll be able to see that light without any change. Even if we were to remove the analyzer and keep it there parallel to the first polarizer, it doesn't make a difference. So essentially we can see that it starts with D because all the light is passing. Now when we slowly rotate it by some angle, there will be some light that is getting cut out and only some of the light that is entering, and only some of the light that is entering uh, the sensor or our eye, the observer. So we can see that among B and A, B is still brighter than A, which implies that the rotation is only a little bit. Because if we take this to be the polarizing axis, and let us say the analyzer axis was at an angle theta, so we can see that what is the amount of light that will be passing through. So I'll just use another color. So this will be the light that will be passing through, and this will be the light that will get cut out. This is cut out, observed. So as a function of theta, it is nothing but the incident lights cos theta. So naturally, after D, we can see that it will be followed by B, which is then followed by A. And slowly, once we make it perpendicular, since it is mentioned here, that slowly it is turned and kept 90 degrees. So it will totally become dark, which is represented by C. So the idea is that now we have a polarizer and we have placed an analyzer that is perpendicular to it, so no light is passing through that. Now, if we introduce some photoelastic model in between these two, in this zone, let me call this the test zone. In this test zone, if we were to introduce some photoelastic model, initially photoelasticity we have discussed, it works on stress-induced birefringence. So initially, when there is no stress, if we just keep that model unstressed, it will not make any optical difference. So essentially, we'll still be seeing a dark screen as we see in option C. But as soon as we stress the model, we'll be able to see that there are, at every point in the model domain, there is some birefringence that is taking place, which will get reflected, because once there is birefringence taking place, there will be light vectors crossing in two directions, out of which component of either that is parallel to the analyzer will get passed on to the observer. So we'll be able to see some patterns there. Okay. So if there are any questions now, I'm happy to take them. Otherwise, I'll keep moving. I'm going a little slow consciously because last time I think I rushed a little, and by around 7:30 or so, I had run out of questions. So I'm going little slow, trying to cover everything. So if there are any, please bear with me. So if there are any questions, you please do bring them up. So okay, so we'll move to the next question. The given schematic diagram shows a monochromatic light passing through a polarizer. So we have a monochromatic light here, monochromatic light source passing through a polarizer and analyzer. Which of these figures represents the output intensity of light for the given arrangement? This is again a variant of the same question, except the key word being the monochromatic light. Now, why this should be monochromatic is something we will see. It needn't be. The thing is that once we have control over the wavelength, monochromatic means single color. So essentially, this implies a single wavelength. Once we know the wavelength, we will see when we develop the stress optic law in the upcoming sessions that our material fringe value, that is the parameter that relates the optics to mechanics. This is actually denoted by a symbol called F sigma. So F sigma. We will see that this also has a wavelength dependence. But nowadays, even the quarter wave plates, they come as achromatic quarter wave plates, which do not essentially get affected. They more or less provide the same sort of retardation given any modulation of the white light. So that is there. Yeah. So ideally, in very controlled cases, we would prefer to go for a known wavelength in order to get more fidelity. Just put it here. Yeah. So monochromatic. So what is kept is we have a polarizer, and monochromatic light is passing through that polarizer. Since this is a generic light source, nothing is specially mentioned about it, so we can take it that it is unpolarized light, unpolarized monochromatic light. So once it passes through the polarizer, hi, good evening. So once it passes through the polarizer, we'll be having essentially only that light passing through like that. And since the analyzer is kept parallel to it, the entire light would pass through it. So we can clearly see that since the entire light is passing through it, this happens to be what we will be observing. Whereas if it were to if we were to place the analyzer like that, that is crossed with the polarizer, then that will be tantamount to seeing this. Because this circular region is the only place where the polarizing sheet is there. The dial around that is just to take the angular measure. So that doesn't have any polarizing this thing around it. So essentially that is what the entire light will get cut out from the analyzer zone. So that is what we will be seeing. This, as we saw in the previous question also, this is equivalent to having a analyzer that is at some angle that is close to 90 but not quite there, and we have a generic white light. And this is the case where we discussed analyzer and polarizer are crossed meaning at 90 degrees, and the entire light gets cut out. This is a case where there is some partial white light that transmits. So this would be essentially, if we were to have the polarizer like that, maybe the analyzer would have been something like that, if this be the datum. This is totally crossed. It's totally crossed. So is this. This is also totally crossed, and this is the parallel arrangement that we have been given. Okay, so if there are any questions, you please do bring them up. Otherwise, I'll keep moving. But understandably, these things are pretty simple, but in order to appreciate how we got to the photoelastic setup, polariscope setup for photoelasticity, it is better that we get a sense of what is going on here. Okay, so I'll move to the next question here. I'm sorry if the size is too small. I'll just try to zoom in now. The given figure, figure 1, this is figure 1, figure 1, depicts the image of word beam as viewed through different arrangements of a polarizer and analyzer. Identify the correct orientation of the analyzer. In figure 1D, here what would have been the arrangement of the analyzer is what is asked. One thing, I suppose this question, yeah, it is clearly mentioned here that first of all it is being viewed through a crystalline medium, because if we just were to take case A, it is just written beam as we would see it. Now the second case B, when it is viewed through a crystalline medium, for example, if we were to keep a crystal over the word beam, then we would be seeing two such words. That is because of double refraction. Exactly. Or by reference. By meaning to, it is just a B is without the analyzer aside. Yes, exactly. So without the analyzer, this is what we are seeing. Now, the first one, we have put the analyzer this way. So as I had elaborated in the first question also, if you have an analyzer with an axis marked like that, it implies that that is the light that is getting passed through it. So generally, analyzer sheets will come with polarizing sheets will come with these markings. So one is kept this way. We are able to see here there are two words. One B starts with that there, and the other one is a little below that. So what they are trying to ask is, if one were placed this way, what would be the orientation of the other? For this, what is the key that we need to understand is, in crystals, birefringent rays, that is the doubly refracted rays, are invariably mutually perpendicular. So they have a planes that are perpendicular to each other. So even in the uh, discussions that will come ahead, we will be marking it this way. For example, if we have a representation like that, what this implies is the undulation, the light is passing in the vertical plane. Vertical meaning out of the plane of the paper. Whereas if we see the other ray would be passing in the horizontal plane. This is the representation. That is in the plane of the screen. So this is in plane. This is out of screen. So these are the two polarization states that are prevalent because of double refraction or birefringence. So once we know that one of the analyzer was placed this way, it is clear to understand that the other one would have been placed that way, which is perpendicular to that direction, because we are able to see the shifted B here. So this is essentially this B, and if you were to see this, so you can correlate with the color in order to get a better understanding. So now this begs one more question, whether there is any preferred orientation of the uh, uh, analyzer that is to be kept. Essentially, it doesn't matter how you keep it, it is just a representation. So ideally, I should be drawing it this way. That is double-headed arrow along that direction, the light will get passed. So it could be A, B, C and D can't be the option. C, we have already seen that it is used in C, and D is datum. It is the same thing as C. So it could be A or B. So yeah, I hope that this is clear. If there are any questions, please do ask. Okay, I take it that it is clear. So let us look at the next question. Was there any question here? And cast that in the view. Okay. Okay, so I hope that is clear. So answer true or false for the following statements. Type T for true, F for false without any spacing, and they have given the reporting style. So I'm not going into that. Anyway, the first statement says the light traveling through a crystal will always be polarized. So yes, this is true because crystal cannot support unpolarized light. Essentially, once any unpolarized light passes through a crystal, it gets doubly refracted, and both are polarized. So yes, this is very much true. In photoelasticity, the model, which is a birefringent material, behaves like a crystal when it is stressed. This is key to understand, that it is only stress induced birefringence. So this gives you another way to check whether your results are correct or not. For example, if you were to do an experiment initially, so we want to understand the stresses developed due to some mechanical phenomena, some loading, generic loading. But we want to ensure that our calculations are correct and no spurious stresses are entering our calculations. So for that, what we can do? in a polarizing in a polariscope, we can simply place the model in an unstressed condition. So we saw that once we have the polarizer like that and the analyzer that is crossed with that, so no light should be able to enter. Let us say we place the specimen here, this being the test specimen, and let us say we have a light source here. So once this polar light crosses the polarizer, we'll have a linearly polarized light, which will get cut out by the analyzer. So ideally speaking, what I should see in the view should be totally dark. Uh, I shouldn't be able to see anything here. You consider that that is black. So this is how I should be able to see because the model is unstressed. But most often, more often than usual, if we take, it depends on the material also, photoelastic material also. But if we were to take some material which has not been used for a while and keep it there, we'll be able to see some colors around the boundary. So we'll be able to see sort of a halo. Why that happens is because of water moisture absorption. So materials like epoxy, these have a water absorption, moisture absorption issue. So what will happen when the outside boundary it absorbs moisture, it will try to expand, whereas the material fiber that is just next to it will not allow it. So there is a stress state that is set up around the boundary. So around the boundary there will be some kind of stresses that will get set up, because of which will get reflected in when you place it in the polariscope. You will be able to see a slight halo which represents some stress in the model. So if you were to then load it, if you want to do a very precise experiment, we should ensure that the model is free of these stresses. How we can ensure is, generally photoelastic models that are sensitive to moisture absorption, we will keep them in a desiccator with silica gel, which will absorb all the moisture and keep it moisture free. Otherwise, there is a process called annealing, where we can subject it to a thermal cycling so that all the stresses get relieved. There are different ways to go about it. This is especially a problematic for epoxies. But in general, if we see other materials like polyurethane, they don't have this problem as such. Okay, so yes, so I digressed a little because in order to make the session more productive, I thought that I'll also take slight detours so that uh, the peripheral aspects also get covered. Because it will be very dry if I simply keep ticking the options and just saying yes or no. So I thought that I'll give you a piece of what goes around as I know it. So yeah, so in photoelasticity, the model which is a birefringent material, behaves like a crystal when it is stressed. Yes, so this is very much true. The ordinary and extraordinary rays are plane polarized, and their planes of polarization are perpendicular to each other. Thanks for the yeah, fine, thank you. So the ordinary and extraordinary rays are plane polarized. So essentially, double refraction deals with double refraction has two refracted rays. So we will name one as extraordinary, one as ordinary, just a nomenclature. So it is measured, and it is a fact that both these are plane polarized and they are invariably perpendicular to each other. So the planes of polarizations of these two are perpendicular. So if we were to have, this is the representation. So if we see double refraction, the single light ray that was unpolarized will get bi bipolarized in the sense that P, I didn't actually Y in B. Yeah. So in B, I didn't understand why birefringent material behaves as a crystal when stressed. I took it as it is. Why it behaves? Okay. No, essentially, how you make polarizers is all materials introduce some optical response. It is seen that these have a, well, that is a good question as to why it behaves like that. I could perhaps study up a little more on this because this will delve into material science. Because, yeah, no, not optical response necessarily. I meant response as a general term, not as an optical response, because opaque materials naturally cannot have a response like that. Some have the, like when we saw for thermoelastic stress analysis, it has a temperature response. So, like that is what I meant. I didn't mean all materials have an optical response in a particular way. But yes, certain kind of polymers, they have this property. Why that is perhaps we might have to go into the physics of polymerization. But it's an interesting question. I'll look it up, and if I'm able to come up with a more elaborate answer, I'll share it in the next session. But as of now, yes, we can see that, see for a fact that for known problems, for example, a disk, we know how the stress patterns look. So if we were to take a polymer and stress it, and we are able to observe that that is the patterns that we are observing, those are indeed the patterns that we are observing, then we take it that it is birefringent and obeying this requirement to be a photoelastic material. Why that is coming about is a subject of material science, and I'll look it up in further detail and get back. So the ordinary and extraordinary rays are plane polarized, and their planes of polarization are perpendicular to each other. Yeah, so you said some knowledge we should. Yeah, not in stress analysis alone. If you see, you will have to go with some knowledge because otherwise we will be reinventing the wheel every time. If we take geometry, for example, we take it that the axioms from Euclid are uncontested, they are true. So that is how we proceed. So it is good to question, but it depends on how much time we have and how much deeper we want to explore. I could stay, in my defense, I could say that I'm in the Department of Applied Mechanics. So once I know the mechanics behind some phenomena, I'm trying to find its applications. So my focus would be more on the application point of view. Now again, there are studies that are being conducted on the phenomena itself as to why that is and how that can be put to use. That is a different kind of study. So naturally, it depends on where your focus is. It is good to explore nonetheless, as far as possible. And with the internet now available, I don't think there is any limit to how much we can explore further. So yeah, if you do get some answers to this, you also please feel free to let me know. I just tried to refresh knowledge about photoelasticity and the thing was unclear, so I decided to ask. Right, right, that's fine. So I can also answer the things that I know currently. In case I don't know, I definitely take it up. I'll perhaps I'll also do some reading and get back to you with some satisfactory answer. I hope that is okay. The ordinary and extraordinary rays are yeah. So we have seen that this is so, and we saw this with the example that we are able to see. This is, by the way, this is from an actual experiment. It is not fabricated. This is from an actual experiment that was done here. So we are able to indeed see that once we place the analyzer in two perpendicular directions, we are able to see either of the refracted rays. So this definitely holds true. So crystalline solids are optically isotropic. uh, isotropic implies that properties, any parameter properties, yeah, these are direction invariant, implying that it doesn't have a preferred direction. So it is not so optical. So the crystalline solids are not optically isotropic. They have optic axis. So it depends on how the light impinges on it. That will tell you how the response would be. So definitely this is not true. Rest being true. So I hope that this is clear. Yeah. Annealing, there are basically, we place it in a, we have a furnace even in the workshop here. In our department, we have a furnace. So there will be standard annealing cycles. If you see, they'll tell you what should be the rate, that is rate of increase of temperature. Then we have to hold it constant for a while, then bring it down, the cooling cycle. So these cycles are generally mentioned for each and every epoxy. These are available in research literature. So we simply take the model and put it in a furnace and subject it to thermal cycling. So this is basically how, yeah. Only thing is, it sometimes when we do it for certain epoxies, it introduces a tint. It will become yellowish. Otherwise, epoxy when we cast it, it is generally transparent, so it will acquire a yellow tint. But ideally, material properties don't get affected much by it. Even if they do, we can calibrate it using a calibration experiment. Yeah, by the fringes, yes, yes, exactly. So in an unstressed condition, it should not show any colors, or it should not transmit any light. When we place it in a plane polarized arrangement, ideally it should not allow any light to pass. In which case, even if the model is not birefringent in a stress-free condition, the entire thing should be black. But if you are able to see a halo around the boundary of the model in an unstressed condition, it implies that there has been some moisture absorption, which is moisture absorption or some residual stress that has been introduced. If we account for that in our calculation, we'll have a better accuracy. Yeah. Okay. So the addition of two simple harmonic motions which are perpendicular and with a phase difference will in general represent result in a trace of a circle, of an ellipse, a straight line, a circle or an ellipse. Circle or a straight line, I'm sorry. That is what the option says. So if we, let us say that we have a wave like that, and then we have another generic wave like that. So if we were to add these two, representative of the tip of a vector representing that wave, we would see that it would represent an ellipse. And the case of a circle and a straight line are nothing but special cases of those ellipses, depending on the magnitudes, relative magnitudes, and a retardation that is brought in. If this be the retardation, if we have a retardation which is equal to a quarter wave, then we will have an ellipse that gets aligned with uh, our basis, and we can appropriately uh, impinge. Let us say if we were talking about light, then if we can impinge light which get equal components, which will give us a circularly polarized light. In case the phase lag is multiples of pi, then essentially we will have a line which will be in some direction. So that is how it goes. This figure I could have drawn a little better. It's fine. Okay, perpendicular and general phase difference leads to an ellipse. So this also is shown if we take one, it is shown in the lecture also, that if we consider one to be, because we have already qualified that to be perpendicular. So if we take the coordinate axis itself, so we can take it some bx sine or cos, however you want to put it, omega t, and ey is by cos omega t plus some delta something. If there is a relative retardation, we can distribute it and we'll be able to see that the tip, which represents nothing but the magnitude of this light vector, will trace the path of an ellipse in general. Under special conditions of this retardation, it will either be it will either fall into being a circle or a straight line. So in general, it represents an ellipse. If there are any questions, yeah, yes, please. Okay, okay, all right. Okay, so I take it that this is clear. Okay, let us move on to this question. A plane polarized light impinges on a crystalline plate, gets converted into two polarized beams of light with a phase difference within the thickness of this plate, as shown in the figure. So we can see that we have a plate here, and once the light impinges, this is just a blow up of that plate, and we are able to see there is a retardation that has been introduced between the two polarized light waves. Uh, there is a retardation that has been introduced through the thickness of this model. So this, from this point to this point, is the thickness of the crystalline plate. So once this happens, we are asking, consider the incident ray is perpendicular to the optic axis. Okay. Axis 1 and axis 2 marked in the figure. They are marked. Identify the fast and slow axis. So what happens when it is perpendicular to the optic axis? Let us look at that in a little more detail. So once we have a crystal or a crystalline solid, so this will have an optic axis, which will be ideally same at every point in that in the domain of the crystalline solid. 1 minute. The screen is not getting reflected. What is the issue? Okay, yeah. So this will have some optic axis, let us say like that. If I impinge light on it in some generic direction, it will have birefringence that will take place, and both these rays will have different directions and different velocities. You can name it the extraordinary ray and the ordinary ray, and these will have different directions and different velocities. Now in two limiting cases where we have the optic axis and the impinging light that is parallel. Let us say if this were the optic axis and I impinge light that is parallel to this, then it goes just unaltered. So whatever light was impinged, it just goes unaltered. Whereas if we were to have the other case where we have the optic axis and the impinging light is perpendicular to it, something special happens that the direction of the extraordinary and ordinary ray remains the same, just that one goes faster than the other, and there is a phase difference that gets acquired through the thickness of that crystal as the light propagates through it. So this happens to be the case where the impinging light is perpendicular to the optic axis, where again it will be plane polarized. We'll have two plane polarized light, and we will have this is the second plane polarized light. Both are traveling in the same direction but with a phase lag. That phase lag is what is represented by delta here, because it is perpendicular to the optic axis, since both will travel in the same direction but one will be faster than the other. So it is just asked that axis 1 corresponds to which axis and axis 2 corresponds to which axis. So we can see that the light vector that is light wave that is perpendicular to this axis 1 is leading the way, and the other one, the light that has passed parallel to axis 2, is has a phase lag uh, by delta. So naturally axis 1 is the fast axis and axis 2 is the slow axis. So this fast and slow axis will also have happen in case of stress induced uh, photoelastic material. Only thing is it will be dependent on the mechanics of the problem, and it will be different at every point, whereas a crystalline plate, if you see, it will have the same response throughout. So that is the only thing to be kept in mind. Now if I were to adjust this thickness such that this delta that has been acquired is exactly equal to some amount that I want, let us say a quarter wave or a full wave, then we will call these wave plates, and these have some specific applications in assembly of polariscopes. So I hope that is clear. If there are any questions, please do ask. Yeah, yeah, that light is polarized. Now, the initially unpolarized light, when it impinges on a crystal, that crystal has preferred optic axis. Now, when we have a light that impinges at an angle to that optic axis of that crystal, we will have birefringence taking place. But that birefringence will take place in a sense that both the light waves will have different directions and different velocities. It so happens, yeah, right, right, yeah, all right, okay, fine, okay. So that's fine. Yeah. This is the one we're talking about. Oh, the one I have drawn. Is it this? Right. Yeah. No. No. The point why what I wanted to show was I could have shown the crystal plate like that, the axis in some generic direction, and light impinging at some generic direction. It needn't be always parallel to the. Yeah, 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 yeah. All right. Okay. So let us look at this question. Identify the correct statements. Crystalline materials are those in which the constituents are arranged in a highly ordered manner. Naturally, this we have been seeing. So there are many examples of crystal, salt, sugar, and we can also see calcite. And there are non-crystalline solids also. So blown glass, if you see, it is non-crystalline. So this is, yes, this is true. So all materials are crystalline materials. That is not correct. Certain non-crystalline transparent materials, notably some polymeric plastics, are optically isotropic under normal conditions. Optically isotropic meaning they have no preferred response, and uh, it is direction invariant, whereas become doubly refractive when they are stressed. Yes, this is what understandably there might be some repetition, but this is what we are trying to emphasize on. So it is fine. Yeah, we can bear with it. So, but they become by doubly refractive or birefringent when it is stressed. Yes, these are all the photoelastic materials. Photoelasticity can be applied only to crystalline solids. If does anybody have an answer to this, whether this is true or false, that photoelasticity can only be applied to crystalline materials? It begs the question, which is the variant of photoelasticity that we are talking about? If it is transmission photoelasticity, then yes, because the principle on which that works is uh, the model behaves as a crystal. Whereas if we see reflection photoelasticity, then we have a birefringent coating that we apply to a model, and the surface strains get transferred to that coating, which will induce birefringence again. And we will have the light source and sensors, cameras on the same side. So this can be definitely applied to materials that are non-crystalline also. Only one variant requires it to be crystalline. So this is not true. Whereas if this were to say transmission photoelasticity, then yes, it would hold. Okay, so on to the next question. In case of a circularly polarized light, the tip of the light vector is constrained to lie on the circumference of a circle. Yes, this is why it is called a circularly polarized light. The tip of the light described random vibratory motion. This is characteristic of unpolarized light. Has a magnitude that varies along the path of propagation. If the magnitude were to vary, then the tip of the light vector, yeah, so the tip of the light vector is this. So from a preferred datum, if we see if the magnitude were to vary, then the length of the light vector also would vary, in which case it cannot trace a circle. So this is not true. So yeah, if C is not true, then D happens to be true. Does not vary along the path of propagation. So this is very much true. So this is a special case of the light ellipse being degenerated to a circularly polarized light by controlling the input light to enter the fast and slow axis in a unequal magnitudes. So if we have a light vector like that, and if we have a plate that has a retardation plate, which introduces a retardation phase lag between the extraordinary and ordinary rays by quarter wavelength, then what happens is our light, whatever be our datum, that the axis of our light ellipse follows that datum. And if we were to place it, if we were to put in light which is at equal inclination to that datum, then naturally both the amplitudes of light become equal with a phase retardation of pi by 2, which implies that it will be circularly polarized. So that is how we make a circularly polarized light. Fast and slow axis. And this is pi by 4. Therefore, not a circle. Okay. So let us look at this question. The given figure shows a light wave, unpolarized, impinging on a crystal, which gives rise to two refracted rays, which are ordinary ray and extraordinary ray. Identify the correct statements in this regard. So this, we have the crystal here, and we have an unpolarized light. So unpolarized we will be representing by actually it has a very generic representation, because it will have components in all directions, not just mutually perpendicular direction, which can only be seen from the diagram I drew. So it doesn't have a representation as such. So which is true in this case? We have two rays. So by this itself we can see if there are two rays, namely extraordinary and ordinary rays, which are not in the same direction, then this begs another question: what would the, if uh, if the incident light is impinging on that crystal at 45 degrees, can we comment about the optic axis of this crystal? It is naturally not perpendicular to the impinging light, nor is it parallel. So that is something to be kept in mind. So the light in this case, incident parallelly nor perpendicularly to the optic axis of the crystal. So whatever we discussed above, it follows from that. All light rays AB, BC and BD are unpolarized. This is not true, because we saw once it enters a crystal, crystal can only support polarized light, albeit there will be two polarized lights, which are mutually perpendicular, and which will have mutually perpendicular planes of propagation, and they can have different velocities. In special cases, they will have the same direction. In other cases, they might have different directions. So this is not true. Only AB is unpolarized, and that is also because it is mentioned in the question. The refracted rays travel with different velocities. Yes, this is true. The planes of vibration of ordinary and extraordinary rays are mutually perpendicular. Yes, this is also true. They travel in planes that are mutually perpendicular to each other. So if we were to represent one by the plane of the screen, the other would be traveling in the out of plane direction. So this is true. The Snell's law is valid for both rays BD and BC. So we have not mentioned which is the extraordinary ray. We have not identified it. So either one of these is the extraordinary ray which violates the Snell's law. So this could be either this or this. So this doesn't hold good. So I hope this is clear. So I'll move on to the next question here. Yeah. So the given figure represents, yeah, yes, please. Yeah, 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 yes, yes. In a generic angle, if it impinges, it will be mutually perpendicular. Only thing is, it will also be traveling in different directions with different velocities. Okay. Yeah. No, the speciality about the light impinging perpendicular to the optic axis is the both the rays will travel in the same direction, but with a phase lag. Here, when it impinges at a generic direction, it travels also in different directions, not along the same line. Yeah, that is the key here. Yeah, no, that's fine. Right. Yeah. Okay. So the given figure, yeah, yes, yeah, yeah. I'm not sure either, but that's fine. It's fine. Actually, anyway, this is a requirement for me, so I'll be doing it. It's quite possible that they might be preparing for something, so that's quite all right. Yeah, yeah. So the given figure represents the light ellipse for a phase difference delta equal to pi by 6. So the retardation, or I should say the relative retardation introduced is pi by 6. Delta is pi by 6. So determine the azimuth angle beta of the light ellipse, this angle beta. So actually this comes from ellipsometry. If we take Ex, let us say, is represented by, oh no, I don't think that is the reason. And even if that be the reason, I don't suppose you should be worrying about it. So that's absolutely fine. So I hope you can just forget about that. So let us say if I were to divide this into two and distribute it among the two delta by 2. So by if I see the magnitude of this light vector would be the sum of the square root of the sum of the squares. So if I were to simplify this, I will be getting a generic expression for an ellipse upon, I think it is some, I will have to refer back, but this can be derived trivially. It's not that big a deal. AXAY cos delta is equal to sine square delta. So this is the expression for the generic light ellipse that we have, and it will be 1 minute, I think. Yeah, I'm sorry. Actually, there's some internet issue here, which is why it logged out. Sorry about the disturbance. I hope you're able to hear me fine. Yeah. Yes, yes. The retardation which is coming, I'm just distributing it equally. I may as well have had one zero and the delta to the other as done in the lecture, but essentially this would amount to the same thing. Yeah. So from this, it follows, we also have a standard result for the azimuth of the light ellipse, which is 2 tan beta, is related to the this by the this thing of amplitudes. So this is the key. Now our idea is to find out what the azimuth of this light ellipse is given these quantities. Now we have been given delta, and if we see these represent nothing but the cap of ax and ay. So if with ax, x in this direction and y in this direction, ax represents 2 units and ay represents 1 unit, which is represented by this point here. So we can simply calculate it. So it will come to tan 2 beta is 2 4 minus 1 into cos pi by 6. So beta, if we see, will come to cos pi by 6 is the answer by 2. It will come to 0.428 radians, which is, of course, this is the principal value I'm saying because tan is multi-valued. So comes to around 24.55. So this, for this case, when the retardation introduced is pi by 6 is 22.5 degrees. I hope I did the math correctly. 2axay minus ay squared. Yeah, axay divide by, yeah, 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 I think this is correct. Yeah, okay, fine. Thanks for the confirmation. Okay. Yeah, yes, yes, yeah. It is azimuth is one and the ellipticity is the other. The ratio, okay, okay. Yeah, yeah, yeah. This follows from the lecture, straight from the lecture. So you can refer, and if you do have questions after that, you can take it from there. Not a problem. Okay, so this is what I meant that optic axis. The given figure shows the representation of a light wave impinging on a crystal for various angles of inclination of the incident light with the optic axis of the crystal shown. The orientation of optic axis is marked. Now there could be a block that optic axis is always parallel to the surface of the crystal. That is not so. It is just that it is shown this way. So it is important to understand that it could be any generic shape and the optic axis could be in any generic direction. It is just that when it is to be taken for an application, naturally we'll make it tangible, but that has no bearing with the boundary of the thing. So that is to be understood. That is one part of it. So now that the optic axis is shown and we have light wave impingement, we see that, okay, what is the question? In which of the above cases is the most suitable to explain the principle behind photoelasticity? So what we see in photoelasticity, why we see colors, we can just, I'll just explain briefly on that, which anyway we will be delving into more detail in the lectures to come. For example, if we have light ray that is impinging on a model. Now this model behaves like a crystal when it is stressed, which means at each and every point in the domain, there will be one preferred fast axis and there will be one slow axis, which will be perpendicular. So when our light that is entering, the controlled light that is impinging on this model, let us say this is that light. So this will get distributed according to the angle based on the fast and slow axis. It will get resolved, and that is what will come. Now if we were to keep our analyzer parallel to the slow axis, we will see that there will be no light that will be coming through. So essentially what happens is, if the light gets totally cut in a plane polariscope setup that is having only two analyzers which are polarizers which are crossed, then it implies that one of the axis is parallel to the direction of the principal stress there. That is why light is getting cut. Uh, Let me explain this in more detail. I suppose I didn't do proper justice to this. Let me take a point. Now I know at that point, let us say that fast axis and slow axis orientation is this way. And at some other point, this, let me call this point 1. At point 2, my orientation happens to be, it just so happens that my orientation is exactly parallel to the x and y directions. Now this is my impinging light vector. Let me draw this in red. So my impinging light vector, it impinges equally on both these points. At point 1, what happens is, this is my light vector, which will get resolved into two components. I'll draw them in green. In the direction of A. Yeah. If we have, yeah, just a moment. Yeah, right. Yeah, I'll come to that. Actually, that is why I delved a little more deep, because what the statement I made, I just want to qualify that a little bit more. So if I have my light at point 1, this is my point 1. At point 1, red line is the impinging light that has got resolved into two components, namely the green. Now, if I were to place my analyzer or the second polarizer parallel to the x, I will still be able to see light that is passing through the fast axis. So essentially, I will be seeing some light there. Now, if it so happens that in this arrangement, my light totally passes through the fast axis as nothing passes through the slow axis, by virtue of that being parallel to it. And if I were to, after this, if I were to place my analyzer like that, so what I will see is dark fringe at that point. That is because the entire light, it got, at that point, the entire light was passing through the fast axis, which got cut out from my analyzer. Mind you that these two are different arrangements. These are not happening simultaneously because I have only one analyzer which I can rotate in one angle. I keep it at one orientation, let us say. I impinge a light that is parallel to my y-axis, and I hold the analyzer parallel to the x-axis, and I see some black bands. What it implies is at those black bands, this point 2 will also lie. Point 2 has principal stress orientation, or the fast and slow axis, because of the stress at point 2 is in this direction, which is parallel to my y. So the light that comes just gets resolved totally into fast and nothing into slow. And my analyzer is parallel to the slow axis, which gets cut totally. That is why I see a dark band. So this essentially gives me direction of the principal stress, because this is uh, the fast and slow axis align with the principal stress directions. So this is essentially my isoclinic. As we saw in the previous sessions also, this is my isoclinic fringe. This will just be black. This won't have any, even if you had a white light or any other light, it will just be black because it is essentially getting cut by virtue of being perpendicular to the placed analyzer. That is the phenomena behind isoclinic fringes. Now, if we were to go to isochromatic fringes, what happens is at every point, since we have stresses that are different, and the light that is impinging, it is perpendicular to the optic axis. So my output light is traveling with different velocities but in the same direction. So I have a same angle with extraordinary and ordinary rays that are mutually perpendicular traveling towards me, but with a phase lag. If that phase lag happens to be uh, some factor of the wavelength of the input light, I'll be seeing different colors. So that is the idea behind isochromatics. Isochromatics due to retardation. I'll just write it clearly. So this is key to be kept in mind. Isoclinic due to fast axis or slow axis, whichever that is, axis being perpendicular to our analyzer. And this is invariably black or dark. We won't see any light is getting cut there. Now isochromatic. It is due to retardation. I don't know, I am. Retardation, which is a function of wavelength. So it will be some fraction of the wavelength. It could be one entire wavelength, in which case we will call that the fringe order 1. It could be 2 times the wavelength of the impinging light. It could be, that will be called the second order fringe. So this is essentially a retardation phenomena which deals with sigma 1 minus sigma 2, the quantity there. This is a inclination, I can say, for the lack of a better word. I'll call it inclination phenomena, which is to do with theta p, which is nothing but the principal stress direction. So this is what is to be understood. For isochromatics, for isoclinic, it doesn't matter. If I have this thing, it will get crossed and it will be a dark fringe, that's fine. But in order for me to get retardation and get some meaningful results out of it, it is essential that my fast and slow axis, my extraordinary and ordinary rays come towards me in the same direction but with a phase lag. Which is the case in which that will happen? It will only happen in case C, where we have the impinging light perpendicular to the optic axis. So C is the only case that is useful for our photoelasticity. So I hope this is clear. Please could you explain repeat settings? Yeah, sure. Why not? I'll do that. I'll just start with this. Let me have a model. I have a light. This is my light source. And let me say that my light source is, I have kept a polarizer and I'm getting only light that is at 90 degrees to my reference axis. Let me call my reference axis X. Now I have my model, which is stressed because of some load, let us say. And I take all through the domain there are points. Let us take 2 points, for example. In this point, let us assume that our principal stress directions or the fast and slow axis is like that. So what will happen at point 1? At 1, light will entirely pass through F and no light resolved into S. This is by virtue of F being perpendicular to the incident light. Now I have my analyzer here. This is X, and let me draw my analyzer in purple color. This is my analyzer, which is kept perpendicular to my light. So at point 1, what would I see? The entire light that went through the fast axis is totally getting cut uh, through my analyzer because my analyzer is parallel to the slow axis. So these two combination leads to a dark spot at point 1. So the collection of these dark spots is isoclinic. Isoclinic fringe, because it won't be that there is one point where the angle is exactly so and the next point the entire light would pass. It will be a band, so we won't be able to decipher, so it will be a wide band instead of a central fringe. So this is called an isoclinic fringe. I hope that, yeah, I hope that I clarified that. Whereas if we want to get rid of this directional dependence, that is why, since we see that one is getting cut because of by the virtue of being perpendicular, if we want to take out this phenomena from our this thing, that is why we will introduce circularly polarized light, so that at every angle there will be some light passing through it to get rid of isoclinic fringes. That is why we go for a circular polariscope arrangement, which we will discuss in detail in the sessions to come. Okay, let us look at this question. Identify the correct statements. In case A, the light travels in the crystal similar to that of an isotropic medium. Yes, because it goes on unaltered when we have the light impinging with the uh, this thing, the optic axis. The ordinary and extraordinary rays have the same refractive index in case of A. The ordinary and extraordinary rays have the same refractive index. Yes, because they go unaltered. Yes, yes. So they have the same. Yes, I mean, yes, that's correct. In case B, the ordinary and extraordinary ray travel in different directions. Yes, because this is at a generic angle, in which case they will be traveling at different velocities in different directions. So yes, this is true. The ordinary and extraordinary ray travel in the same direction with the same velocity in case C inside of the crystal. Yes, and this is the arrangement which we indeed want for our in the same direction with the same velocity. I'm sorry, this was key. It said in the same direction. Yes, this is very much true, but with the same velocity. This implies that that would be unaltered, which will only happen in case of the thing being parallel to the optic axis. Uh, this is not true. It will have a phase lag, which is our retardation. This retardation, what we will do is we will normalize it with the wavelength. Let us say delta is my retardation, or delta test is my retardation at that test point. I will normalize it with my wavelength, and I'll call this as a fringe order n, which is a dimensionless number representative of that fringe. So in case my retardation at particular points is equal to half of the wavelength, then my fringe order at that point will be 1 by 4. That is the idea behind it. If it is equal to one wavelength, then it will be fringe order 1. It's like that. Okay, so I take it that this is clear. Yeah, so we'll just move on to this question. Mark the following sentences as true or false. Enter T. Okay. 15. The ordinary ray obeys Snell's law. Yes. Unavoidably, there is some repetition, but that's fine. The refractive index is larger for extraordinary ray than the ordinary ray when incident light is perpendicular to the optic axis. Is this correct? Yeah. They'll be uh, it'll be traveling with the no, if the incident yeah, if the incident light is parallel to the optic axis, then yeah, then it goes unchanged, but here it is perpendicular to the optic axis. Yeah, essentially same direction, but with different velocities. Yeah. So refractive index is a tensor of rank 2. Yes, which is basically why we are able to correlate refractive index with our stress tensor. This is also direction dependent, which implies that it requires two directions at every point to be specified. So refractive index is, yes, it is a tensor of rank 2. And when we speak of refractive index, yeah, it won't be shown. Actually, we have come across many quantities which we take it to be scalars, but which are actually tensors. Refractive index being one of them, the coefficient of thermal expansion being the other one. That is also essentially a tensor because it has directional dependence. For isotropic materials, this waters down to being the same quantity. But no, it is not shown. This is also taken at face value because certain things are skipped in order to see the application part through. So this won't be shown, but I'm sure there is enough literature on it to refer to. Yeah, okay. So a crystal cannot sustain unpolarized light. Yes, this is true. The uh, it cannot sustain because the light sustain meaning transmit. Essentially, this what yeah, transmit is the yeah, exactly. So it cannot sustain, which is true that it can't. Okay. So, okay, let us look at this question. again, the actually I was wondering as to why some of the things were not covered threadbare, because ellipsometry is totally altogether a different whole topic in itself, and under the purview of extensive research. So certain things which were taken from ellipsometry have been presented here in order to emphasize the idea behind the light ellipse, and how with the help of a polarizer and a quarter wave plate alone we can develop light ellipse of any azimuth and any ellipticity. So in order to emphasize that point and to develop the tenets of photoelasticity, this was introduced. But certain things invariably have to be taken at face value. But nonetheless, there is enough literature that is available on it. In fact, quite extensive literature is available on ellipsometry. So this again is directly, it follows from the lecture. So why that is something that you can refer the lecture, and also if need be some additional literature might be required. So why this handedness is important is because when we were doing conventional photoelasticity, where we were doing it for point by point, every point in the model domain uh, by observing. Rather, it was conventional was rather I would say it was qualitative rather than exactly being quantitative, because of the subjective nature of what we are observing. Whereas now the photoelasticity, that method has matured quite a lot, and we have digital cameras, and using digital image processing, we can decipher what is the fringe order and the stress information at each and every point to great degree of accuracy by using methods like phase shifting methods. So in those applications, this handedness of the ellipse, whether the light that is propagating, it is propagating in the right-handed sense or the left-handed sense, it becomes important because elements, optical elements like quarter wave plates, they essentially introduce some error. And in order to nullify that error, we might have to have the handedness reversed, which, so to speak, cancels out the effect of one. So in that respect, it is quite important to understand that is the place where this handedness plays a major role, which is why it was briefly touched upon in the lecture. So the addition of two simple harmonic motions which are mutually perpendicular and having a phase difference results in different states of polarization for different values of phase difference. Now here we are essentially talking about light vectors. Let me make that clear. Identify the state of polarization corresponding to the set of phase differences being delta, for the given set of figures. Enter the alphabet. So what we generally observe is from our equations. I had written that equation somewhere. I'll just copy that. Yeah. So what we observe here is when our retardation that is introduced by some optical element or a crystal plate or our model, it if it is it will depend on delta. What is the retardation introduced? How our light ellipse would look like. So it so happens, it follows from this equation also that if you introduce, let us say, delta that is multiples of pi, then essentially our light ellipse will degenerate into a line, so which will become a linearly polarized light. So this is nothing but your half wavelength, half lambda. So, and we also know from that angle, I'll just copy that also, just a minute. So depending on delta, we will have ellipse with specific ellipticity, which can degenerate into a circle or a line or a general ellipse with different azimuth angles. So if it happens that our uh, our retardation that has been introduced is a multiple of pi, then it will our ellipse degenerates into a line. And by having wave plates that are introducing half wave retardation, which are called half wave plates, we can essentially have control over rotating that linearly polarized light. Whereas if we were to introduce plates which have a quarter wavelength, I'm sorry, pi by 2 is quarter of a 2 pi wavelength. So this is a quarter wavelength retardation. When we have that, essentially what happens, the fast and slow axis of our crystal plate, which is introducing quarter wavelength, our light ellipse coincides with that. Now, the how we rotate is how we control the azimuth. So what happens is if we have a plate which introduces quarter wavelength retardation, we have the light ellipse that is coinciding. The axis of the light ellipse coincides with the fast and slow axis of that quarter wave plate. Now, if we were to place that quarter wave plate in such a way that the impinging light has equal components along fast and slow axis, then we get something called a circularly polarized light. So this is to emphasize on the point that just by using a linear polarizer and a quarter wave plate, I can develop uh, light ellipse of different ellipticities and different azimuths. So that is the key behind this uh, question, essentially. And handedness, again, it comes from ellipsometry as to how to identify handedness. Uh, so why this becomes important in digital photoelasticity that I've explained in order to cut down the errors. So when we have a retardation that is essentially between 0 and pi by 2, which is the quarter wavelength, not equal to, mind you, it is not equal to pi by 2. When it is this way, essentially it follows from the lecture that we will be having, we, we will be having this, yeah, light ellipse would be like this, and our handedness would be this. Handedness is, okay, no, actually it again depends on, okay, uh, well, this is also discussed in the lecture. Perhaps there might be a difference between what we are considering it to be clockwise and counterclockwise, because if we see in the lecture, what is considered to be counterclockwise is marked as left-handed. If in general, if we see counterclockwise is pointing out of the plane of the paper sheet, so we take it to be right-handed, but it is marked in the other way. So I would recommend that you just have a look at the lecture once. If it is following the opposite convention, then perhaps this mismatch of identifying it makes sense. And in that way, okay, okay. So whichever one leads, that decides whichever one leads, and the other which retards, that is what decides the handedness, I suppose. So once I would suggest that you just have a look at the lecture as to what is the sign convention that is being followed, because clockwise and counterclockwise again would get flipped if we were to take the positive to be going into the plane of the paper as opposed to out. So there could be some mismatch there, but essentially we could deal with this question based on the azimuth now, as of now. And as for the handedness, I would recommend once you watch the lecture also. So B and D is the choice we are having here. So as per the conventions discussed in the lecture, it has to be D. So yeah, so now coming to a quarter wave, when we introduce delta equal to pi by 2, what happens is that this thing just degenerates to, I'm sorry, this one. Yeah, no azimuth. Essentially, our axis is what will be this thing. So if this is going in this direction, this will be H. And then it will start rotating the other way as we go from pi by 2 to pi. It will be this way, this way. Yeah, so it is E. And as soon as we cross pi, then we see a reversal in the handedness. It will just be following the same pattern, but with a reverse handedness. So pi to 3 pi by 2, uh, pi to 3 pi by 2. Yeah, so this is the opposite. Yeah, so it will be A. And then at 3 pi by 2, it will just be the same case as pi by 2, no azimuth, but in the opposite direction. So if we see, this is the direction that is given as opposed to H. So this will be G. And between this, it will rotate again in the opposite direction. So this would be B. Now this happens to be the special case. This is no azimuth, and so is this. Now what happens when we once there is no azimuth, what it implies is we have a retardation plate which has a fast and slow axis, and our axis of the ellipse is aligned with the fast and slow axis. Now the ellipticity of that ellipse is only controlled by how the light vector gets split into this fast and slow axis. If we place it at 45 degrees to the light vector, the fast and slow axis will have equal components, which implies AX would be equal to AY, in which case we will have circularly polarized light. (26) at delta equal to 3 pi by 2. This also will be, yeah, exactly. This also will be circularly polarized. Only thing is, it will have flipped handedness. So this will also be the same. Yeah. Now this question has, if delta equal to 2 pi, then the state of the incoming light is elliptically polarized, circularly polarized, linearly polarized, or elliptical or circular. It'll actually, when it is multiples of pi, it just happens to be a linear polarizer, but this has the capability to rotate the input light. So if we have a half wave plate that is placed, we can actually rotate the linear light. So let us say if I have a polarizer at 90 degree and I have a half wave plate and I rotate it by 30 degrees, then I will have linear light coming through that wave plate at 30 degrees. So it has the capability to rotate and transmit. This is true for half wave plates. So yes, so this will be linearly polarized. So yeah, so actually I've run out of questions now. But anyway, today I went a little slow. Yeah, difficult question. Yeah, in the sense that Yes, some background of ellipsometry, either introduction to ellipsometry is required, or perhaps one might have had to see the lecture. But it is okay. It is good to brush these things up once, because if we go to the application part, when we come to Jones calculus, we will be able to see as to how we can employ these in order to get, for example, what zone calculus is essentially just a matrix representation of a optical element. So in a circular polariscope, in a polariscope, essentially, we have a light source. Then we have different optical components. Each of those optical components can be represented by a matrix. So that matrix, once we operate it over the impinging light, that is the exit light of the previous element, we'll be able to gauge what will be the exit light at our end. So in order to understand all that, we need to understand how a rotator and retarder works. So that was the emphasis behind this. So I hope this has been clear. So if anyway, I have run out of questions now. So if there are any other questions, thank you, thank you. All right, thank you very much. So other than this, if there are any questions, please feel free to ask, or you can also ask it in the forum. And yeah, problem. Yes, yeah, yeah. Okay. May I know where you are finding that link from? Actually, for the, yes, yes, yeah, yeah. Yeah, no, understandably, the thing is, initially for the first week, there was some delay in from the Swayam portal in order for them to upload that sheet. Once you have that sheet, I'll be populating only that sheet. So last week, as soon as the session got over, the very next day, it got over on Monday. So Tuesday morning, I had uploaded the link, and I had updated that sheet. So you can just check once the very next day. I suppose it will get uploaded, because to link that sheet to the portal page, that must have taken a time, but that is only a one-time affair. Once we have that sheet, that is where I'll be uploading going forward. So you can definitely refer to that from there. So I hope that is clear. And yes, thank you for the enchanting questions. It was quite a fruitful session for me also. And some interesting questions about what causes it to be birefringent. I'll also take a note of it. Yeah, thanks. So if I do find answers, I'll be sure to share it with you. Thank you. Other than that, if there are no questions, I'll call it a day. Thanks. Thank you. Yeah, bye. So just to emphasize on the point about the isoclinics, for example, if we were to take this point, I can see that the isoclinic angle I have given is 25 degrees. So I can see a black band that passes through this point like that. And if I were to see on the right side, I can see that my polarizer is oriented at an angle of 90 plus 25 degrees. And I have linearly polarized light which is parallel to that passes through, and my analyzer is crossed with it and nothing passes through that point. I can see that the response is nearly zero, which is why I see a black point. Whereas if I were to see the same thing in color with a white light source, I'm able to see that this point is still black, which implies that this is a function of direction and not the wavelength. So this is what the isoclinic is. about. Whereas if I were to see some other point where I have a circular polarizer arrangement, I can see that I have on the right side, I have a polarizer, I have a quarter wave plate, I have another cross quarter wave plate, and I have an analyzer. So the light that comes from the polarizer is linearly polarized, which becomes circularly polarized because of the presence of the quarter wave plate. And the yellow point here indicates the model under consideration, which is essentially the disk that we see on the left side, which follows. And then once we have the crossed quarter wave plate, we again have the light getting converted back to linearly polarized light. And since my analyzer is at some angle, and this is also a function of the retardation that has been brought about by the model, at this point, at this specific point, I'm able to see that there is some light that is getting transmitted, which essentially implies that this is a function of retardation. So these show the isochromatic fringes. While this black band, it shows the isoclinic fringe, which is superimposed over the isochromatic fringe. So both of these have been taken from this software developed at Digital Photomechanics Lab, IIT Madras. I just covered this example so that the idea behind the polarizer analyzer crossed combination and the retardation which I had explained becomes more clear. Thank you.